Welcome to the next video in measure theory and probability. This is video 9 on the set of points of convergence, and it corresponds to part 1, chapter 1, section 3 of the textbook. Now we're going to prove a theorem which briefly says that if you take a sequence of measurable functions, the set of points at which the sequence converges is a measurable set, right? So if you take, take this sequence of functions, look at each point, and decide whether or not the sequence of functions converges at that point. If it does converge at that point gets added into this set A, and otherwise it does not. Right, so A here is the set of points at which the sequence converges, and we will claim in this theorem that this set is a measurable set. And what that sort of has the effect of doing is telling us that, that in a sense we can kind of restrict our function to this set. Not in the usual sense, though. What we're really going to say is that we can build this function h, and if you evaluate h at some point that is in A, which is to say some point where the sequence converges, then we use the value of the sequence. If you evaluate at any other point, then we simply send that over to 0. So we can build this function h, and h is a little bit like the restriction of the function to the points where it exists, in a sense, the limit exists. And so anyway, we're going to show that this function h is a measurable function. Now, the proof is going to construct a few objects, and I cannot honestly, really to me, the most perplexing one, I can explain the proof, but I really wish I could tell you how anyone ever came up with this in the first place. I like to explain proofs by sort of taking the next natural step and then the next natural step after that, so that everything sort of flows and makes sense. But this function g really seems to kind of come out of nowhere, and I really cannot say why, as a matter of learning proof techniques, I cannot tell you what lesson to learn in this particular case, because I just don't know why you should think to come up with this function. But anyway, we'll just go ahead and accept that we're just going to define this function and use it to do this proof. So the function is going to have domain E and range the two-dimensional space of extended real numbers. And for any given point x in E, we will send it over to the point. So this is a point, kind of ran out of space. So this is the first coordinate, this is the second coordinate. So we're sending it over to the point, which is, has x, the left coordinate, the lim inf of the sequence, and the right coordinate is the lim sup of the sequence. So there's our function g. Again, I can't tell you, why anyone thought to use this function g. There you have it. Of course, now I think this next part, once you have the function g, I think it's somewhat clear that we must be doing something with those points at which the lim inf equals the lim sup, because of course that's where the limit exists. And so I think we're fairly naturally interested in this set delta, which is the set of all points in, this should be the extended real numbers. But this is the set of all coordinates which have the same first and second coordinate. It makes this diagonal line in the extended two-dimensional plane. And so we're going to be interested in where this set delta intersects certain other, sets and so on. So anyway, so here are two objects. Now, the first thing that we're going to claim is that G is measurable. So let's see why that is. Now, we're going to pick a set that generates the Borel sigma field on, on the extended real numbers squared. So what is the generator? Well, we're just going to, somewhat arbitrarily, but not entirely arbitrarily, pick the collection of all intervals that go from some finite real number out to infinity. So that collection, in fact, the collection of all of the products of such intervals, right? So we're going to take all Cartesian products of such intervals. That's going to be the collection that generates the sigma field. I'll leave it to the viewer to prove that generates this sigma field, but I haven't proved it to myself, but I don't think it should be too hard. Anyway, if anyone wants to see the proof, let me know, and I can make a new video for that. In any case, that's what we're going to take to be the generator. And so what we want to do is we want to take any arbitrary I1 and I2 such that I1 is one of these intervals, I2 is another of these intervals. And we want to prove that the pre-image for G on this product is measurable, right? So that's our goal. Since we're trying to show that G is measurable, we're trying to show that the pre-image on this generating collection always gets you a collection of measurable sets. So that's the goal. Now this pre-image, let's think about what it means, right? It means that G of X is inside the interval, right? So just to give an extra step here, this writes X is in this pre-image if and only if the image of X is in the product of the intervals. And to be in the product of the intervals means that the first coordinate, which is the lim inf, needs to be bigger than the lower bound defining the interval. So long story short, this, right, the lim inf of F1, or sorry, Fn, sorry, where did I come up with 1 and 2? Anyway, these should be n's. So the lim inf of the Fn sequence should be bigger than A1. And then thinking about G of X, which the second coordinate of G of X is the lim sup, and that's supposed to be inside of I2. So that means that the lim sup should be bigger than A2, the lower bound of I2. So that is just completely equivalent to what this pre-image is, right? This set here is equivalent to the pre-image, is equal to the pre-image. Now, because this set is defined with an and, it's totally natural to split this up into an intersection, which we know to be a good step, because after all, we're trying to show that certain things are in a sigma field, and we know sigma fields are closed under intersection, so breaking it up into an intersection is a good idea. Now, this individual set then just becomes the pre-image of the lim inf function on the interval from A1 to infinity. I think that should be fairly clear, but if you need to, pause the video and think about it, possibly prove it to yourself if you need to. But then likewise on the second intersected set, and each of these, right, we already know that Fn is a measurable set. We know that the lim inf of a measurable function is a measurable function. So this lim inf Fn is itself measurable. We are taking the pre-image of a measurable set. Since the function is a measurable function, this means that the pre-image is a measurable set. Same story down here. So we know that each set is measurable. We're intersecting measurable sets, and therefore the intersection is measurable. Now let's notice that delta, right, we're basically going to claim that A is the pre-image of G on delta, right? So hopefully it's kind of making sense how all these components are coming together, right? If A is equal to this pre-image and G is measurable, then if we show that delta is measurable, then we've got the pre-image of a measurable set, therefore it must be measurable. That will be how we show that A is a measurable set. So that's the big picture game plan, right? And the only piece missing at this moment is to show that delta is measurable. So why is delta measurable? Well, keep in mind the sigma field that we're talking about here, right? It is the Borel sigma field, and therefore it is generated by the open sets. Well, this delta fairly clearly is a closed set. If you'd like me to prove that, I can prove that. Leave a comment if that's what you want, but I think it's clear enough that any curve, any continuous curve in two-dimensional space is a closed set. And so delta is a closed set, and as a closed set, its complement is open. That's from just simple topology. And because the Borel, right, we're talking about the Borel sigma field on R2, meaning that all the open sets are generators for the topology. So that means that this open set delta complement is one of our elements, right? It's a measurable set. It's in the topology, and therefore it's one of the generators, and therefore it's in the sigma field. So this delta C, it's measurable. That's kind of the upshot there. Well, if delta C is measurable, and measurable sets are closed under complement, then when we go back to delta, we have another measurable set, and the proof is finally complete. Okay, so having shown that A is a measurable set, we're going to move on to show that H is a measurable function. To do this, we're just going to grab any arbitrary set from the Borel sigma field on R. Actually, I suppose it should be R bar. Now we're going to break this proof into two cases. In the first case, we'll consider the possibility that 0 is in F, or sorry, is not in F. And in that case, if 0 is not in F, then necessarily H, right, like if you pick a point in the pre-image, right? So let X be in the pre-image. Well, then therefore H of X is not equal to 0, and therefore necessarily, by definition of H, right? Remember that if the lim does not exist at this point, then we send H to 0. Well, that must not be what's going on in this particular case, and therefore the lim must exist, right? So effectively, when H does not take the value 0, we must be talking about the case where the limit exists. And moreover, because we're talking about the pre-image of H on F, then we must be talking about that value being in F. So this point X, right, like we were considering this point X that is in the pre-image of F for H. And I have effectively argued that that X must be in A, because the limit must exist at this point, and also that X must be in this pre-image of F, because of course, right, like H is sending X over to F. And so the most immediate thing that we could write about that is that if we took the pre-image of this lim Fn of F, that X is contained in that, if we wanted to write it like that. Now we are instead talking about the lim sup. We could, it doesn't actually have to be the lim sup. We could also have said the lim inf, but we're just talking about the lim sup here because the lim sup must be equal to the lim, right? If the lim exists, then it's equal to the lim sup. And we already know that the lim sup is a measurable function, right? So that's why we're switching to talking about the lim sup, is because we know it's a measurable function. And therefore, since we are taking the pre-image of a measurable set for a measurable function, then therefore this whole thing must itself be a measurable set, right? So we now have that, that this pre-image of H on F is the intersection of two measurable sets, therefore it is a measurable set. Therefore, right, the upshot from here is that, or sorry, we're not yet at the upshot. But we have shown that under the assumption that 0 is not in F, we get a measurable set. Now we have to further show that, what happens if 0 is an element of F. Well, if 0 is in F, right, so let's consider that case over here. If 0 is in F, it would be nice if we could leverage the thing that we just proved, and so we could say the following, right? Like maybe it would be nice to think about the complement. So let's think about the pre-image of H on F. Now that is the same as the pre-image of H on F complement. And that is the same thing as moving one of the complements to the outside. So this move where I am sending one complement outside, that's a valid move, which you can prove, right? Like in general, if you take any function, like what do I want to call another function? I guess just to make up some random function symbol. If you ever take the pre-image of some function on some set AC, right? So I'm just making a general point, right? Phi could be any function, A could be any set, so on and so on, right? Like this is meant to be a general point here. So any function, any set, if you ever have this, it is equivalent to phi pre-image A complement on the outside. So this is a general fact about sets and functions, and I won't go through the demonstration of this. Hopefully you, the viewer, can fill it in. If you want me to fill it in, I'll make another video later if you leave a request in the comments. But for now, I'm just going to accept this principle. And so effectively, what we now have is that this is, right, like, now F complement is one of our Borel sets, right? Because the complement of anything in a sigma field is another thing in the sigma field. So F complement, that is something in our Borel sets. It does not contain 0, because if F does contain 0, then F complement does not. And so here we, from the earlier part of this proof, this is measurable. And therefore the complement of a measurable set is measurable, so we have that this is measurable. So now we have it in all cases, right? So when 0 is in F and when 0 is not in F, we know that always the pre-image of H is a measurable set. And this finally concludes the demonstration that H is a measurable function.